Hello grade 11s and welcome back to another video with me, Miss Martins. In today's video, we're going to be looking at atomic combinations, part of the grade 11 chemistry syllabus. We'll be looking at past paper exam questions. So I'll be doing this past paper. We'll be looking at questions like these, as well as questions relating to this graph. So you don't want to go anywhere. I give teacher tips. Don't forget to subscribe for lots more videos like this in the future. I do physics, chemistry, and math. Let's jump right in. So first things first, we've got ammonia, NH3. And by the way, ammonia is a common compound that you are asked about. Sometimes they just say ammonia and you are expected to know that it's NH3. Just keep it in mind. Ammonia and hypochlorous acid, both examples of covalent compounds. Our first question says, define the term bonding pair. Definitions are an essential part of chemistry and physics. You need to know them off by heart. You can find them in your exam guidelines or your CAPS document or your ATP. So this definition is as follows. Two electrons, so a pair is two electrons shared between two atoms in a covalent bond. And when we draw Lewis dot diagrams, we can often see the bonding pairs and or the lone pairs. Take note how the words that are underlined, those are keywords. If you leave out those words, you could risk getting 0 for your definition. 2.1.2 wants me to draw the Lewis structures for the following molecules. Now these are Lewis diagrams or Lewis dot diagrams. I have plenty of videos on how to draw these. If you need more help with them, check out the links down below. But let's do it first of all for ammonia. Now how you do Lewis dot diagrams is as follows. You look for the number of valence electrons that each atom has. And a quick way to do that is to look at the Roman group numerals on the periodic table. So in the case of ammonia, NH3, the N, nitrogen, is bonded to the hydrogen. So nitrogen is over here and it has 5 valence electrons. Hydrogen is over here and it has 1 valence electron. So these numbers over here, the Roman group numerals, tells me how many valence electrons my atoms have. So NH3, we're going to have a nitrogen with 5 valence electrons. 1, 2, 3, 4. You place 1 on each side and start at the top again, 5. We're also going to have 3 hydrogens like that. Each of them have 1 valence electron. 1, 1, and 1. Now, drawing these diagrams are not necessary at all. They are only required, they're not even required. The only reason I draw them is to help you see what needs to happen. See if we need to form a single bond or a double bond and who needs to join where. So now how this works is that each of the atoms wants to reach noble gas configuration, noble gas structure. Nitrogen has 5 valence electrons. It needs 8 in total. So if it has 5 and it needs 8 in total, how many more does it need? It needs 3 more. It needs to share 3 with other atoms. That is the reason why it shares with this hydrogen, and with this hydrogen. Hydrogen, all of these, they each have 1 valence electron. Now hydrogen only needs 2 valence electrons to be full to reach noble gas structure. So how it works is as follows. We draw the nitrogen in the middle with its valence electrons. Remember it had 1, 2, 3, 4, 5 like that. It needs 3 more. So it's going to share 1 with this hydrogen, 1 with this hydrogen, and 1 with this hydrogen. It is best to keep their symbols separate. The reason why is because now I can see that the crosses are the electrons that come from the nitrogen and the dots are the electrons that come from the hydrogen. So I always tell my students the one in the center can get its own symbol. So the nitrogen is in the center, it has crosses. The hydrogens on the outside, they have dots. I hope that helps. Let's do the other compound, which is HOCl. 3 atoms that are bonded covalently together. If we look at the periodic table, H again has 1 valence electron. Oxygen is over here. It has 6 valence electrons. Chlorine is over here. It has 7 valence electrons. Now remember, all that you need to draw for me is the final structure. So for example, for ammonia, all you had to do was to do this for me. That's all I needed. I didn't need this intermediate diagram, but it helps me. So I'm going to do the same for HOCl. So I've drawn the hydrogen. It has 1 valence electron. Oxygen has 6. Count the dots. You'll see that there's 6. Chlorine has 7. Now, what you need to do is ask yourself, how many electrons does it have? How many does it need? There we go. Now remember, hydrogen only needs 2. in total to reach noble gas structure. So it has 1, it needs 1 more. So therefore 2 in total. Everything else needs 8. So oxygen has 6, it needs 2 more, that would make 8. Chlorine has 7, it needs 1 more, that would make 8. So now you need to ask yourself, how can they share in order to help each other reach noble gas structure? Because we know that they are covalent compounds, which means they need to share electrons. Okay, they share, they do not transfer. Very important. So oxygen has 6, it needs 2 more. What that means is it could potentially share one of the electrons with the hydrogen. So what is going to happen is this one electron over here is going to get shared in that spot with the oxygen. Okay, now oxygen has 6, but now it's sharing with the hydrogen, so it has 7. Oxygen still needs 1 more electron. But think about the chlorine. Chlorine has this electron that it can share with the oxygen in that spot. Then think about it like this. When the hydrogen, let me make myself smaller, I'll show you. When the hydrogen shares this 1 electron with the oxygen will in turn share that 1 electron with the hydrogen. So the hydrogen becomes full, the oxygen has shared that 1 electron. Then the oxygen shares this electron with this chlorine, which shares this electron back with the oxygen. Chlorine will then have 8 because it's sharing that 1 extra electron that it needs. Oxygen shares both with the hydrogen and with the chlorine, so therefore it is full. So this is how your final diagram should look. Something like that over there. Take note how there was an open space over here for oxygen to share an electron, so chlorine slotted into that space over there, if that makes sense. There was an open space over here for hydrogen to share its electron, so hydrogen slotted into that space over there. If we have to count the electrons that belong to oxygen, it would be 1, 2, 3, 4, 5, 6, 7, 8. The crosses now also belong to the oxygen because they're sharing. Hydrogen has 2 electrons, it's full. Oxygen has 8, it's full. And chlorine also has 8 if you count, it's full. A lot of my students also ask me, ma'am, is it okay if my diagram looks like this? Yes, it's perfectly fine. Here you see my hydrogen was on the left and chlorine was on the bottom. It doesn't matter. Here my hydrogen's on the left, chlorine's on the right. It doesn't matter. As long as you can see, that's a bonding pair, that's a bonding pair. So oxygen has 2 bonding pairs. And then if you take a look here, that is a lone pair. That is a lone pair. So oxygen also has 2 lone pairs, 2 bonding pairs and 2 lone pairs. And it's actually good that we started counting bonding pairs and lone pairs, because the next question actually says, write down the number of bonding pairs in ammonia. So let's go back to our diagram of ammonia. Ammonia we did over here. So if you count the number of bonding pairs in ammonia, that's a bonding pair. So the bonding pair, remember, is shared between 2 atoms. So it's 2 electrons shared between 2 atoms in a covalent bond. So it's 1, 2, 3 bonding pairs. So my answer for that is 3. B says the number of lone pairs on the oxygen atom in HOCl. We just counted that. Let's count it on this one. So remember, that's a bonding pair, that's a bonding pair. This is a lone pair and this is a lone pair. We also counted it here. Remember, we said 1 lone pair, 2 lone pairs. So 2 lone pairs on the oxygen. So that answer there is 2. Then the shape of the ammonia molecule. So back to ammonia. When determining the shape, what they mean by shape is the shape determined by this model. The VSEPR. I call it VESPR, the VESPR model. You get linear, you get bent, you get tetrahedral, trigonal pyramidal, trigonal planar. I have a whole video that goes over the different shapes and how to tell what shape is which, but the best way is to determine the shape from the general formula. And the general formula is based on how many bonding pairs we have and how many lone pairs we have, essentially. So here we have a central atom, and in the general formula it's represented by A. It's bonded to 1, 2, 3 other atoms, so it's AX3. And we've got 1 lone pair over here, and a lone pair is represented by E. That is the general formula, which will dictate what shape I'm looking for. And you need to know that that general formula corresponds to the shape called trigonal or trigonal, however you say it, pyramidal. pyramidal. Trigonal, pyramidal. You can also think of it like 3 bonding pairs, or if you bonded to 3 other atoms, if the central atom is bonded to 3 other atoms and it has 1 lone pair, it'll always have the trigonal pyramidal shape. And just by the way, the molecular geometry or the shape, the molecular shape of this one, this would be AX2. It's bonded to 1, 2 over there, and then E2. This would in fact be bent, or what we call angular. I know we won't ask that in the questions, but just so you know. My next question is which bond, the NH bond or the OH bond, is more polar? Give a reason for the answer. Now, when speaking about the polarity of bonds, we need to work out the electronegativity of the bond to determine if it is polar covalent, non-polar covalent, or ionic. So, determining the difference in electronegativity between N and H, and then the difference in electronegativity between O and H will help me determine which one is more polar. So difference in electronegativity, how we calculate that is we look at the electronegativities of each atom. So I'm going to list it here quickly. N, H, and O. Let's quickly read it off the periodic table. It's always the sideways number. The key over here tells me that. So if we look at hydrogen, the electronegativity is 2.1. So I'm just going to write that there, 2.1. Nitrogen is 3.0. Oxygen is 3.5. Okay, 3.5. So when we work out the difference in electronegativity, if we're looking at the NH bond, we take the bigger one, so N and H, bigger one minus smaller one. So 3 minus 2.1, that gives me 0.9. And if we compare it to the OH bond, the oxygen is bigger, so that is 3.5, minus the hydrogen is smaller, 2.1, and that gives me 1.4. Therefore, the OH bond is more polar, and the reason why, it has a greater difference in electronegativity. There we go. My next question wants me to write down the type of intermolecular forces. Now remember, intermolecular forces are not bonds. Intermolecular forces occur between molecules. So when they say intermolecular forces, I want you to think London forces, which is one of the van der Waals forces, or dipole-dipole, or hydrogen bonding. Those are what should be going through your mind. Not ionic bonding, covalent bonding, and metallic bonding. Those are bonds. We're speaking about intermolecular forces. So write down the type of intermolecular forces present in both ammonia and hypochlorous acid. Now, if you know your intermolecular forces, again, I have a video telling you the different types of intermolecular forces linked below. But if you know your intermolecular forces, you will know that if you have a nitrogen-hydrogen bond and a oxygen-hydrogen bond, or a hydrogen-fluorine bond, which isn't the case in this question, but it also counts. And I summarize this by calling it HNOF, HNOF. So if hydrogen is bonded to nitrogen, like in ammonia, or hydrogen is bonded to oxygen, like in this acid over here, or if hydrogen is bonded to fluorine, like in this case over here, then your molecule, between your molecules, what you will have is something called hydrogen bonding. So both ammonia and hypochlorous acid have hydrogen bonding between their molecules, and also London forces, because London forces exist between everything. But the answer they're looking for in this question is hydrogen bonding. 2.1.6 says when ammonia dissolves in water, remember ammonia is NH3, when it dissolves in water, which is obviously H2O, the ammonium ion, NH4+, is formed. What type of bond forms between the ammonium molecule and the hydrogen ion? And that, if you know your work, is a dative covalent bond. I have a whole YouTube video on dative covalent bonding, how it works, how to draw your final Lewis dot diagram, and I actually do this very exact example, so go check it out if you want to see more on that. 2.2 is a graph that everyone loves to hate, but it's really not a bad graph. It's actually simple once you understand it. It says graph of potential energy. So potential energy is on the y-axis over here, potential energy, versus internuclear distance, distance between nuclei. during bond formation is shown. And this is a little bit of a weird graph because we tend to read the graph from the right to the left because it basically shows the process of where two atoms are very, very far apart, and that starts here on the right, and then when they approach each other, what happens to the potential energy, how it sharply decreases until they form a bond. So a bond is formed at the lowest dip in the graph, for lack of a better word, the crest, the trough of the graph, this over here, or over here, depending on which curve you're looking at. So this would be where the bond would form for B, and this would be where the bond would form for A, and then you push the atoms too close together and then they start to repel, and that's why the potential energy shoots up again. So that's basically the graph. Again, I have a video going over the whole graph in detail if you want to check it out, link below. But we need to understand how to interpret the graph and how to read values off the graph. First, they ask you to define the term bond energy. Another definition that you just have to know. Bond energy is the energy needed to break 1 mole of a compound's molecule into separate atoms. Very important, and just look at the marking guidelines. If any of the underlined words are omitted, so if you leave it out, you minus 1 mark. So if you don't say per mole or 1 mole, and if you don't say into separate atoms, you lose 2 marks, you get 0. Now 2.2.2 says which curve A or B represents the formation of a double bond between oxygen atoms. Briefly explain the answer, 3 marks. So saying A or B will get you 1 mark, and then explaining will get you the last 2 marks. So if you read again what they say in the beginning, they say potential energy versus distance between the nuclei of 2 oxygen atoms. So one of these curves is representing the formation of a double bond. The second curve is representing the formation of a single bond. The first thing that you need to know is the difference between the double bond and the single bond. What we say is the double bond looks like that, obviously. The single bond looks like this. The double bond has a higher bond order than the single bond. So the more bonds, the higher the bond order. And just by the way, you should know this, the more or the higher the bond order, the stronger the bond is. It makes sense. A single bond won't be as strong as a double bond, and a double bond won't be as strong as a triple bond. So the higher the bond order, so if we go from single to double or double to triple, the bond energy increases because it's a stronger bond. So bond energy increases, and bond length usually decreases. Okay, very important. Why would bond length decrease? Because the stronger the bond, the closer those atoms pull together. I hope that makes sense. I do once again have a video explaining this in detail. So essentially what we need to be doing in this question is we need to figure out which of these curves represent the bond that has the lowest, we're looking for which one is a double bond. So we need to look for which one shows you the largest bond energy or the strongest bond and the shortest bond. So if you look at both curves, let's take a look at A firstly. A over here, if you go up this way, if you go the vertical distance, that will tell me the bond energy. Okay, this distance over here. That means that the bond energy of A corresponds to that number over there, 494. Okay, it's negative because a bond is being formed, but 494 kilojoules per mole for A. That's the energy. If you compare that to the energy for B, look at curve B. Curve B is over here. Here's the bond energy. It's that number over there. Again, the vertical distance, 142. So which one has a stronger bond energy? Definitely A. And if you take a look at the internuclear distance, or the distance between the nuclei, which tells me the bond length, you will see that A has a much shorter bond length than B. This is the bond length. How do I know that? Because it says distance between nuclei. So if I have one nucleus over here, one nucleus over here, the distance between their nuclei when they form a bond over here, that is the bond length. And if you look at A, when the bond is formed at this low point in the curve, the internuclear distance between A is 121 picometers, 121 picometers, which just by the way is 121 times 10 to the negative 12 meters. Just by the way, you times 10 to the negative 12 to convert to meters. And for B, it's 148 picometers. So which one has a shorter bond length? A. So A is definitely the double bond. It's the stronger bond. So this is how you would explain it when the bond order increases. So when we're looking at a double bond, which has a higher bond order, then the bond length decreases and bond energy increases. 2.2.3, write down the bond length of the bond represented by curve B. Now, we already did this, but just as a recap. So I've highlighted curve B in green for you. This over here, so there, the lowest point of the curve over here, if you read this way, that will get you the bond energy for B. I don't want the bond energy. That's on this axis. Don't want that. And if you read up here, 148 picometers, that gets me the bond length. So your answer, 148 picometers. I hope that this has been helpful. Please let me know what else you want to see in the comments below. Remember to subscribe if you haven't yet. It means the world to me. When you click subscribe, you become one of my YouTube students officially. So please do that. And I can't wait to see you in another video very soon. Bye, everyone.